And so with Len's keynote, we're going to have a slightly different format. So Len is the CEO of XKL and one of the co-founders of Cisco Networking. This is his second NANOG keynote. He's really offered to answer questions from the audience about anything. But we wanted to get him started off. He's been talking with us a little bit about the challenges of scaling the network, scaling network capacity further. And then as you grow in speed, you go faster. What are the challenges of doing it at greater scale? So we're going to ask Len a couple questions here and then open it up to the microphones for Q&A. So thank you, Len.
Happy to be here.
So Len, you mentioned the statistical multiplexing or StatMuxing is a way to grow packet networks and data networks and optical networks going forward. What's the history of StatMuxing in the telecom industry?
Well, it almost seems silly today, but in the 60s we had a problem with these computer terminals. Yes, actual serial terminals. And if you had a number of them, you often ran out of wire or you ran out of ports on a computer to connect them to. These ports were once rather expensive. Again, seems silly, but that's how it went. So people decided, well, we can build this interesting device which had less expensive serial ports and ran a whole group of them down a single channel over to your computer. You'll recognize this idea. In particular, it was very simple. You took typically a 4 or 5-bit number from the port, appended that to the character, sent it down a common channel, and there you were. Some people experimented with systems that essentially just put one character time slot after another, what we call time domain multiplexing today. But the more interesting ones, if there was nothing to send, the channel had an idle pattern, and if you had something to send, well, you put this port data pair on the line and went on. Okay. Not very complicated by today's standards. Something about this inspired two folks in places that it wasn't supposed to happen. In particular, one was working for RAND and the other was working for the British Post Office, to think about whether this sort of idea might be extended a bit to send computer data. Well, nobody thought you'd care to do that. I mean, that was a crazy idea. That was, interesting, but had no future. I certainly had a vice president at Bell tell me that the data stuff had no future and I should work on something involving voice. Get the joke? It was the 60s. Okay. And of course, the development of packet switching is why we're here at all, because that idea underlies all the modern computer technology. I remember giving a presentation one time to a room full of slightly sleepy people at 5 in the afternoon that I eventually got their attention about the striking difference in economics that I predicted. Once again, that was amusing only in retrospect. At the time, it was certainly uncomfortable for me. And them, it turned out. So, what you're seeing on the screen is two identical drawings, because the idea is the same. You took this very simple idea, run it a bit forward, turn it into whatever data you want, actually, and on we go. Now, rather than imagining those triangles were so simple, imagine that those are switches or routers. What's the difference? Well, at some level, there isn't. Now, building a big network out of these sorts of devices, or indeed switches, probably isn't a good idea. I don't think I need to go on about that one. Folks in this room probably understand what that would do. So, we won't. Nonetheless, as speeds go up, have you noticed? Oh, okay. Well, let's talk a little bit about the statistical aspect to it. And a big deal about the original Ethernet is it was a spatially distributed statistical multiplexer. Now, the statistical aspect of it caused some folks considerable fright. There are lots of folks in the world that are concerned about randomness and just don't believe in statistics, in effect. And other solutions are more appealing to them. That was the great token ring versus Ethernet controversy all that time ago. But I think the world is now comfortable with statistics and the properties being useful commercially. So here's what we typically do with our networks today. How does this picture not represent effectively every network we all run? Well, it does. Okay. Well, what do we pay for and what do we get for it? As the port speeds go up, the technological challenge of producing a useful switching device goes up as well. Just right today, are a lot of your router vendors out there trying to sell you terabit ports? Show of hands? Okay, so they're not quite there yet, are they? Something about that 7 nanometer process that they
might want us to pay for them.
Oh, well, yes. It's not a charity. And how will they be there for next year if you want another one? No. I think we're all comfortable with the idea that we have to pay for our thrills. That's certainly true. In my view, the best thing you can do with an expensive big frame router with very fast ports is to put a good number of them together. And the routers that we call core routers that have access to the global routing and hence forwarding information, every switching decision they make is of high value. That is something that we can use more effectively by, in effect, unfortunate juxtaposition, building a statistical multiplexer in front of each of those ports. Everyone, I think, accepts the horrible finding of the 80s when we discovered the challenging statistics of computer data, that there is no finite amount of buffering, that we will not overflow over some time period. I can go on about the mathematics of how that evolved, but it's simply true. No amount of buffering can handle every computer data load. We don't build networks that do that, although the bad thought that started with some very slow links has been carried forward, and many devices truly do victimize the customers with buffer bloat. So when something goes wrong, when things are working well, it feels good. When things go wrong, oh my. Well, I recommend we not do that and have a bit more discipline as the port speeds go up. So we've experimented with various, there's a point to all this, is an interesting background, but at Xscale we have been experimenting with this, and we have built some products that embody these simple ideas. I call them level 1.5 products. If a time division multiplexer would be a level 1 product and a switch is a level 2 product, well, we're somewhere in the middle. We don't really look at Ethernet much. It's frames, that's fine. And we don't have MAC addresses on these ports. We have our own internal addressing scheme that makes things simpler. But one of the things it enables you to do, well, first you can simply do this, which is to take fiber channels, fiber colors, and get a little more average use out of them if you're comfortable with it. If you configure things for one-on-one bandwidth, you get exactly no non-statistical failures. In fact, you don't get any failures at all. As you become a little more comfortable with this, you can typically take a little bit of oversubscription because it just isn't going, as a realistic thing, happen more than once a day. And that's probably okay. Well, one of the other things you can do, remember the SONET ring recovery that is pretty commonly used? The problem is the stranded bandwidth. You have half of your ring unused at any given instant. This kind of statistical idea can be used as a type of recovery. So in normal operation, about half of your traffic goes each way around the ring, falls out the other end, and no one's probably within a few milliseconds of fiber any wiser for the difference. The backhoe strikes, the fading occurs, and your statistical weights rebalance in such a way that all the traffic tries to go down one way around the ring. It's the usual sort of multi-classification scheme. So the folks that you say ought to go all the time, and the best effort guys do get a little worse service. But depending on the statistics and the loading, not that much worse. Our experience is it is often imperceptible to end users that all of a sudden we're doing 100% oversubscription on one of the ring links. Okay, that's an interesting result for us. Another thing you can do, some years ago, one of the large European telecoms set a challenge to say, okay, by 2020, using 2020 technology, which we had assumed would be 7 nanometer silicon, it's turned out to be a little slower than that, but it still comes out about the same. What would it take to produce 30 million 10 gig customer ports? That's not without, I hope that doesn't surprise anyone that a nation state might have 30 million 10 gig customer ports sometime in the future. Exactly when might be harder to say. Well, using the conventional redundant router, edge router type architecture, you can build an effective network that will do this. Ignoring for a moment what that network itself would cost, it has one shining, or I should say glowing, flaw. It consumed about 1/3 of Western Europe's power capacity. I assume various of us are having trouble keeping the air cool. But that's a staggering development. And what it tells you is, well, maybe we have to do something a bit simpler in some stages of it. So with some of the developments that we've done, we think you can build a spatially distributed, resilient, that is to say, cut links won't be a problem, router port front end. So what we're going to try and let you do is take each of those expensive terabit router ports and access them from a physically distributed set of client ports, all the while taking advantage of some of the statistical effects to do things like ring recovery. And we can do this for considerably less power than another layer of what amount to edge routers. We also believe that the result is fully effective. And because of the scale of these networks, we don't have a flat network issue. It's also true that it's not really a flat network. You really are going from the client ports towards a single router port for each of the colors, and that makes a number of the problems seen in flat networks not likely to occur. something for you to think about this morning. What are you getting when you buy a switch or a router? And as the speed goes up, is there a way to get that same effect for less power and probably less money while you're at it? So that's what I prepared to say. What I'm really interested in is what's on your minds. You can ask anything. I may not know, I often don't, but what would you like to hear? What would you like to know? Let's talk about where your shoes pinch, what makes your head hurt this morning. Well, not all of that really, please. That's perhaps too much information.
All right,
If we have folks who would like me to talk about any particular thing, ask particular questions, please come join the microphones and we'll have a go at it. Gentlemen, you can chime in at any time.
Yeah, so then obviously with Ethernet switches, front-ending routers, and so on, we do have some of that statistical multiplexing, but that's the case where you can get not only increasing scale, but reduce the power by doing it at the optical layer and leaving out some of that technology. So you're talking, first of all, on the technology side about what can you leave out, and then how can we architect our networks differently to scale faster, use less power, and be more efficient.
I wish I said it that way.
Nicely done. So with those Ethernet switch ports, as opposed to the router ports, what am I getting? First of all, what am I paying for in my power budget, in whatever ASICs and merchant silicon underneath, and what would I be leaving out if I did that at layer 1.5?
Well, everyone has some fond story of a switch helping them, and you do get that. You get the ability to run the links quite independently. You do get elasticity because they do buffer the device, pardon me, they do buffer the streams. Of course, the problem is they all do have too much buffering, and they're not very disciplined about what happens when those buffers overflow. They're assuming they put enough in. Well, we discovered again by the mid-'80s, we knew that was impossible. So you ought not try. So without some care and some configuration options that I don't see in any switches that I deal with, you really have no good way of controlling that level, another level of buffer bloat. And you didn't get anything for it. Unlike some of the routers where it was an important decision, the things that the switches do are in some sense trivial decisions. And you're just not getting your money's worth for the cost of the buffer. Power, they're pretty good because you're getting, the vendors who make many of these things believe they're going to sell them in vast quantity, so they're starting to be willing to pay the $12 or $15 million mask charges for the narrow geometry silicon masks. That produces a pretty good effect. You do get a lot for your money. Let's not offer excessive criticism here. It's just that making too many of your users visible to each other in this type of flat network, having too much buffer and delay in exchange for not very important decisions doesn't seem so worth it. In fact, it's a bad trade-off to my mind. You are paying too much with the buffer bloat and some of the misbehaviors that you get from switches. It's just too high a price.
So I've got a question. When we started using switches in internet exchanges, one of the first problems we ran into was head-of-line blocking.
Oh, sure.
And even today, we start to see that in router architectures from time to time, where you're trying to send between two unloaded ports, but trying to go across 4 25 gig lanes or whatever, which also include one port that's oversubscribed and dropping packets. So is that still a concern? Obviously, first with Ethernet switches, and then doing in the optical domain, if you're doing many-to-many, is there a risk of?
Gosh, I thought we solved that in step-by-step exchanges when I was with Bell. Oh dear. So much for the land of the Erlang distribution. Head-of-line blocking shouldn't be happening today. I thought that everybody who aspired to build computer hardware knew how not to do this. In fault-tolerant systems where there is enough damage, you might very well still be vulnerable to it. But in systems that are operating normally, the fabrics need to be accelerating fabrics so that you just don't get this. And you need to distribute your scheduling so that you don't make the bad decision to get to the limited resource that you congest. Right, that there is still head-of-line blocking astounds me. It just shouldn't do that. So I don't know whether that's useful, but I'm sitting here sputtering that the head-of-line blocking is still an issue. That's a long time ago that should have gone away.
Len, you mentioned one potential use for optical statistical multiplexing is to help with an issue, a challenge such as 30 million 10 gig ports, yeah. Right? You don't have to run all those through Ethernet switches and routers, which are can consume a tremendous amount of power. What about some of the novel uses to deal with the challenge of higher speed interfaces? So where today, obviously 100 gig is a common standard, but trying to get to 200 or 400, where can optical statistical multiplexing help us with some of those challenges?
Well, it's easy enough for us to make the line speed go up without changing your port interfaces much. You have a much harder problem when you come back to all those hosts with, are you really going to get 200 gig and 400 gig and 600 gig and 800 gig and terabit host interfaces? And who wants to make switching products that interface to every one of those? Now, there is a nightmare scenario for me, which is we get to those speeds and it's widely disseminated on hosts because it's the end of days, that this is the end of technological progress. I'm more optimistic than that myself, so I don't think that's going to come real soon. But if that's what happens, that's my interpretation of the events. We should be looking for the apocalypse because we're running out of our ability to make it go faster. It's gotten harder, I concede that. It has gotten tremendously harder, but we ain't dead yet. All right, we have some questions.
Yeah.
What do you think we should do?
I think the center mic was the first question.
Good morning, Matt Petak from Yahoo for at least another 4 days. Len, you mentioned layer 1.5 is kind of it's not Ethernet, but it's not just optical. I'm curious about your thoughts on another very famous layer 1.5 protocol that a lot of us have been using for kind of shoehorning the how do we scale things without needing more power and more heat in devices, and that's the use of Mpls. Do you see Mpls as being able to more widely solve some of those power, heat, sucking layer 3 router problems, providing that multiplexing function at layer 1.5 without having to kind of go back to the very, very basic model of multiplexing that you see here in the diagram? Is Mpls actually a good, reasonable solution for these problems?
Depends on how you want to think about it. Mpls can have a place in the world and it can be effective. People take what is a fairly good idea and sometimes overuse it. The problem that you generally get with Mpls is a command and control problem, which is I know I can engineer a reasonably large Mpls network for single failures. I'm not sure that it's readily possible to dynamically deal with multiple failures. It's harder in a number of ways than it looks, and the command and control structures that I'm aware of would find that difficult. So actually, we looked at MPLS. By the way, MPLS is a descendant of the so-called TimeNet protocols, if anybody remembers those. With the stack of destinations, and every time you have a reroute, you push the stack, and those ideas have been with us for a long time. But still, the temptation is to build too big a nationwide network. Our vision here with the way we've done things is, you might get to 32 or 64 nodes on the line side, and you can probably tolerate a node degree of, you're going to get lots and lots of client ports, but when you look at the node degree on the line side, you're right now getting to a dozen 100 gigs in a single switch might be pushing the elastic boundary of wisdom. It has an elastic boundary, but you can overdo anything. And I hate to say it, but there are MPLS networks in existence today that really have crossed the line as far as I'm concerned. If the network gets big enough and spatially diverse enough, there's always going to be multiple failures present. And the joke about the internet is we're the principal cause of failure in the internet. We got the passwords. Those typos, oops. Nobody here has ever done that, I am sure. So I don't have a lot bad to say about MPLS, but caution and restraint are really required, more so than almost anything else.
Thank you.
Right, stage left.
Hi, can you guys hear me? Hi, this is Arif with Arista Networks. Mostly a comment for the gentleman who was concerned about head-of-line blocking. Just wanted him not to be discouraged, depending on the chip and how the chips are arranged. This is a solved problem, just like you said. So that's all I had to say. Thanks.
Okay, a vendor that tells me that they think about head-of-line blocking and they regard it as a solved problem. Not that it's impossible to occur. As I say, if you're building a highly fault-tolerant system, there are patterns of failures that can still, that have impaired. Many people have built distributed resilient switch fabrics, so that things can fail and still continue to function. Under some of those circumstances where you no longer get an acceleration through the switch, if your decision process isn't distributed far enough forward towards the ingress, you could still see it in some failure circumstances. But generally speaking, a fully functional switch, correctly architected, simply shouldn't do this. I don't know what else to say. It's just sort of, like I say, sit here sputtering.
So what about the security of networks? That's something you've talked to us about before. And obviously, a lot of the content providers have invested a fair amount of money in encrypting the communications between their data centers because the client communications are encrypted, but that was a weakness where they sent data across what they felt were private networks and cable systems, and it was in the clear. So what's the right place for network operators on the transmission side to encrypt client communications? What are the security concerns? What recommendations do you have there?
Well, I don't know how deeply people want to go into the issue, but fundamentally, my answer to this is if anyone cares about the security of their data, you need to have done memory to memory per connection key exchange encryption, and that what shows up on the wire already is fully encrypted by diverse means. So it's a much harder cryptographic issue because you face this variety of crypto systems and an enormous number of keys. Now, we do see folks wanting to say, well, you know, that's all well and good, but look at what you can do by header analysis. Look at all that information that's there that you could possibly recover by analyzing the data streams? Well, there is information. First, with every computer security issue, you need to know three things. What is the value of the thing that I'm protecting? What is the time period that that value is retained? And who are my adversaries? If you do not know these things, you're probably not ready to make a recommendation on what to do. So, troop movements, very important for the course of a few battles. After that, well, that's history, and it's apparent to anybody who was on the ground watching. Your list of nuclear targets, much longer importance, much more important, and you must assume that your adversaries have all the resources in the world and they're limited only by the state of the art in their mathematics and technology. Ah, yes, that word, mathematics. When you come to look at whether your crypto system is any good, we really only have one tool, and that is the mathematics of computational complexity. Anything short of that is a delusion on our part. Are people aware that the public key crypto systems rest upon an unproved assumption about the difficulty of so-called either digital logarithms or factoring? We are all depending for key exchange security on something that I cannot say if it is secure. That's just how it is. I cannot say. So if you want a more secure system, you have to go to other ciphers. They're less convenient, and you discover that the principal challenge with this is really key management. So back to the other question, which is, well, shouldn't we just put some sort of simple-minded bulk line encryption on our systems? Well, if it's simple-minded, who are your adversaries? You know, it's not actually easy to tap a fiber, I know how, but you can do it, and if your adversary is sufficiently robust, they do too. So if that's who you're fighting, where's your provably secure crypto system, and how are you going to implement it at multi-hundred gigabit speeds? Well, I can do some of that, but I'm not sure you want to pay either the power or the price. So truly, you need to know the three things: the value, the duration, and the adversary when you consider computer security of any sort and broad discussion. I can certainly say more about it if people are interested, so ask some more questions. We have another gentleman, far stage right.
Yeah, this is Bill Manning. The adversary is me, or you, as the case may be, whoever is initiating it. The question I have is there was a fair amount of interest in what was called buffer bloat, where everyone decided that it was appropriate to add buffering capability at pretty much every step of the way in every handoff, and that buffer management turned out to be a significant problem. And we see with the TDM, you're buffering in the wire. With statistical multiplexing, you're buffering on inputs and outputs.
And wire.
And, well, yes. Do you see buffering, particularly at increasing signaling rates, to be an issue? And if so, how do you fix that?
Oh, it's certainly an issue. The idea with a correctly configured StatMux is that, yes, because of the nature of the distribution of the data, you're going to lose some data. We already have accepted that as soon as we drank the Ethernet Kool-Aid. I see a lot of Kool-Aid drinkers in this room. By distributing what is a fair amount of data, but not too much of it in any stream. What you can do with the statistical multiplexers is get a fair amount of the benefit of switch-like buffering by doing basically stream-based buffers off towards your inputs, and to not try and have these big buffer pools that mean, well, there's two things. You have to have a means of, the wild man stream from overwhelming parts of the pool. And you have to have means to prevent, again, off normal circumstances from producing really nasty delays. Simpler to deal with it by spatially distributing the buffers, having a modest amount of them, and taking your losses there. You're going to have losses. The question is, where will you take them? And what damage will have been done when you do take the loss? So my view, and it's been for some time, is to put the buffers widely distributed in small quantity in individual sense and take your losses there. I hope that answered a part of that question.
Center microphone. Okay.
Matt Petak, Yahoo again. So you mentioned encryption before, and I want to circle back to that briefly. You talk about the foundations of it being in mathematics, much of which is unproven. I'm curious about your thoughts as a corporate CEO in terms of the notion of copywriting or patenting the mathematics behind encryption to limit the scope and use of it. Do you think encryption is something that should be unencumbered and freely available, or do you think it's okay for companies to lock down and protect via patents and copyrights?
Well, I've had this discussion with a number of governments over the years, and a lot of views differ. My view is that if you cannot publish, your cryptographic work, have it fully known by every adversary for all of their capability, and that the security of your system depends upon your mathematics and your key management, because in the end it does depend on those things. You might as well admit it. You can hide things for only a short period of time. How long did we hide the secrets of the nuclear bomb? Think of how well we did that. And that same human failing is what will defeat you. Even Apple's lawyers can't actually keep that stuff hidden in time. It's a delusion to believe that in the end your crypto system can remain hidden. It will depend solely on the quality of your mathematics and the operational resilience of your key management. I don't know whether I've had that view for quite some decades now.
Thank you.
I hope that answered the question. It's not a very, it's not a cheery answer in some sense, but it is, as far as I can tell, true.
So we got two at the stage left.
Patrick Gilmore, Markley. I was wondering your opinion as we make things bigger, faster, better, sexier, whatever. Is the real dilemma going to be the size of the pipe, or are we going to get bigger lanes? I mean, can we get to terabit without chopping it into 1,000 1 gigabit lanes? Or is it going to be the power that's going to stop us from making truly massively scaled networks? Which one is going to hit us first?
Well, we can produce today 100 gigabit per second client links without much in the way of, getting to 50 gigabit per single electrical stream. We can do that today. I have the instruments and things in my laboratories to do that. Maybe not such a commercially good idea right now, but another lithographic spin or so, and it'll be okay. So right now we get to 100 gig by having 10 gig, well, which we break into 20 virtual lanes for reasons that are now seeming quaint in terms of if you look at the committee slideware, but we could certainly get to a terabit with 10 100 gig streams. Okay, so that may not be the bigger problem. As you start to go too much beyond that, and I can talk about why this is so much more difficult. Actually, I'll hold that as a footnote. I'll get to that, I hope, in a minute or so. Trying to build a switching device that treats the ensemble of the bandwidth as a single logical stream and maintains what you might imagine to be good order will eventually become impossible. You're going to have to give up some of the properties that we hope to provide for our customers, but you give them up only in a medium scale, and that contains so much data. I mean, think about how many bits fall on the floor per microsecond and when someone breaks a fiber with a bunch of 100 gig channels on it. That's 50 milliseconds seems like an eternity in terms of the bit bucket filling up. So I am optimistic that we're going to have the ability to make the electrical signaling go faster, realize that we're crossing another threshold, that if you'll recall, it was painful to go it was easy to go from 622 to 2.5, 622 megabits to 2.5 gigabits, because with care, the same technology, electrical technology, would do it. When you went from 2.5 to 10, did you recall how long that took? The physics changes at about 3 gigahertz. The world becomes more distributed. You get dielectric losses being important. You get radiation. The world changes again about 30 gigahertz. It turns into what we all knew. We joked in the 60s about the glowing golf ball and that everything was a lossy dispersive channel and that was the way it was. Well, you get past 30 gigahertz, which means 60 gigabits. The world is lossy resonators connected by dispersive transmission lines that also radiate. Oh well, it just got hard, or harder.
Good morning. I'm Simeon Mete from Berkeley Lab. Folks who build cloud data centers have the opportunity to control access to the medium, access to the channel from the endpoints. Do you see this as influencing the kind of gear that they might buy or you might manufacture, so that we have two kinds of network gear, one for the internet, one for inner data center networks?
People who are already specializing things for cloud services, when you get to be at the scale of AWS or Google, there's a lot of people in this world that will simply say, well, what would you like us to build? We'll build anything you want. And that's happening now. Now, by the way, when you talk about control, careful who you buy your computers from. I hope people in this room have internalized the utter horror of Intel's security screw-up. If anybody in this room hasn't understood how frightening this truly should be, go research it and pay attention. This is by far the worst security mistake ever made in mass-produced hardware. How does Amazon know that AWS hasn't been owned already? How do you know that your instance is private at all? Just today, if you use Intel computers, you cannot say that. Oops. So, careful what you pray for. The vendors will make, when you're buying at that scale, anything you want. If they're wise enough and ask for good things, they get a good competitive product at a good price. If they ask for the wrong things, or the vendors make mistakes in ways that they can't detect, you have the potential disaster. Oh well, that's, you know, it's like the people building your big dams. If they don't do it right, things go wrong. Anything else in that? I mean, I don't know how to directly answer the question other than that way.
Robert Smith, WAN Security. Good to see you here, Len. Hey, I wanted to ask, we see a number of line rate offload cards, crypto for higher level protocols. Can you talk to us a little bit about the feasibility of doing that on an Ethernet layer?
You might kind of dropped out there a second. Fellas, looked like it was an echo canceller that deconverged, or?
Try it again.
Try again.
All right. We see a number of offload cards on the market right now that focus on higher level protocols. Can you talk about the feasibility of putting those in some of the DWDM at an Ethernet level?
Okay. Recasting the question a little bit, it's where should protocol processing get done? And generally speaking, the wisdom has been to put it as far towards the fringe of the network as is feasible, but no further. And by that I mean we don't have our users doing the entire stack themselves, probably for the simple reason that they do a bad job of it. Operating system folks still do bad jobs of that occasionally, but they've gotten pretty good. So that's much of the answer. And when you talk about offload cards, what you've really constructed is a closely coupled computing complex between your operating system driver and the computers on your line cards. You can do that, but it does take a certain amount of architectural finesse to make it be robust enough to be worth the effort. These things can be quite hard to make robust. Each of them, look at it this way, each of the protocol stacks that we use has had a tremendous amount of experience. Many things have gone wrong. There have been enormous ranges of network speeds involved, and there have been enormous ranges of applications run through them. When I'm a bright young hardware designer and I want to build an offload card that's going to make it all go gee whiz bang fast, my protocol stack, if it's to actually make things go fast, has essentially zero experience. And so, how good am I? Well, sure, you know, everybody's young and immortal once, but the truth is it can be quite difficult to produce a robust implementation in this distributed computing, distributed but closely coupled computing environment. It's not easy to do well. If you have a specific problem, if you have elephant flows in a supercomputer or things of that sort, I think you can do it. I think you can do it effectively and it will work. But doing it in general is vastly harder and takes longer than the hardware's life as being of value. At least that's the view I have. I could be convinced otherwise, but there you go.
Okay, thank you.
Gentlemen, did we tire them out?
I think
Either we bored them and put them to sleep.
I've got a non-technical question for you, Donnie. Technical.
Yeah, just actually tying in that last question about upper level protocols, and you'd mentioned that this is operating, you have a model that's operating kind of at 1.5. How do you reconcile the fact that you might not have sufficient information about the framing of the signal that's happening optically? Is that a concern for you? Like, how do you know when to chop up and multiplex the optical signal safely?
We've chosen to do things on a Ethernet frame basis. That means that under most circumstances, you will have a thing that you recognize with a start symbol, some addresses and things. We don't look at the addresses, but they're there and they have ends with a frame check sequence. That provides convenient multiplexing point for the optical side. We're not quite limited to that, though. You can still have other protocols that run, so long as they do provide that same start and end delimiter. What's inside is, unless you ask us to look in there, we don't look in there, really. If you wanted to put something else on there, that's fine, but the general low-level Ethernet signaling of idle line, idle symbols, start symbol, something you should care about, end symbol, idle line, is all that we really require. We're able to sort of add our own, and they look a lot like things that were added for fiber channel and stuff, our own out-of-band signaling to give you the addressing. So we add this, not that unlike Mpls overlay. Other than that, it's the world in the optical coherent communications side of the house is not stable enough to get broad inter-vendor interoperability. If you buy your coherent module from different vendors, they may have a mode that they might interoperate in some reduced performance sense. But to get the full performance, you really have the same guy at each end. And we don't want to get in the middle of that battle. That's a battle of the chipset giants.
How should a 1.5 device treat a damaged frame, a partial frame? Should it be performing checksumming before it puts it on the wire, or should it be cut through as much as possible?
We just pass it through. If we have to add a VLAN header to an Ethernet frame, we don't recompute the FCS, we update it. The mathematics isn't particularly straightforward, but it is possible to not recompute the FCS, so you still have end-to-end protection of the data. And so if we wrap something in a VLAN sense, we are careful to only update that FCS, not to recompute it. So if something has gone wrong, you'll know at the other end, and hopefully some counters are going to go up.
I think this may be our last
All right.
Sorry, I know it's not fair to ask a question like this with a short amount of time. Don Lasher, F5. Curious what you think about machine learning and path optimization and the potential for either accidentally or intentionally poisoning that learning, but particularly like machine learning and path optimization.
Well, machine learning, if there's such a thing as natural intelligence and there's such a thing as natural stupidity, if you, by analogy, say there is artificial intelligence, there must be such a thing as artificial stupidity. Well, if it can be intelligent, why can't it be either deluded or misinformed? I have no problem with that. If you're dealing with something that's like real intelligence, it'll have all those same properties. But machine learning does have, there's lots of places where we can use it. One of the problems that you get is if you're dealing with something that's actually very important, so much of modern machine learning is essentially opaque. We can't tell you what for sure will happen in an absolutely novel circumstance. I mean, I remember an early ARPA project that was looking for tanks in the bushes, and they got to a pretty good result on their training set. The problem is what it really recognized was a sunny day. The tanks were only there on sunny days. Okay, artificial stupidity. I'm with it. What was the other part of that question?
It was whether or not, oh, he's coming back. You want to come back and repeat the end of the question?
Yep.
Interference, I believe.
Sure. Sorry, the second half of the question was, what do you think about the potential for either accidental or intentional poisoning of that machine learning, right? If we get to a stage where a lot of that path optimization is being done by machine learning, we've kind of raised our hands and we trust it, right? So there's a potential for both accidental and intentional poisoning of that data.
Well, I believe that's true. My view, my framework of that was if what we are trying to make is intelligence, even if it's not a general intelligence, we can mislead any intelligence and it can be deceived. If we're not honorable in what we ask these machines to do, well, it's no more honorable than brainwashing. We can be brainwashed. Why can't our artificial intelligence be brainwashed? You have a responsibility to not torture your artificial beings. Well, may not have put it that way, but at some point, Kurzweil thinks that we're going to cross a threshold where they'll be at least as good and then eventually better than us. Perhaps we'll have to learn respect. Probably not what anyone wanted to hear there either.
Do you have any closing comments you'd like to make, Len?
Well, I'm pleased to see the organization continue to grow and prosper. I'm just delighted that we get a good collection of people who want to be responsible for what's become an extremely important aspect of modern life, to come together and to learn and share problems and solutions. I'm an optimist. I think the future can be improved. So here we all are. It's our job. There's nobody here but us. Thank you all. Good morning.
Thank you very much, Len.
Oh, you're welcome.